And his research is very broadly on networks and CS and their interaction with society in all kinds of large-scale systems. He is a member of more or less all the national things you can think of: Academy of Science, Academy of Engineering, Arts and Sciences in Boston, the Philosophical Society. He has served on many national committees, and he is, has many fellowships. Among the prizes he got is the Nevanlinna Prize, the ACM Allen Newell Award, the ACM Prize in Computing, just to name a few. But with that, I don't want to take much of his time. I'm really looking forward to your talk.
Thanks very much. All right. Yeah, thanks very much for the invitation to come speak here. So I want to talk about some things I've been working on actually it began with some joint work with my longtime co-author, Senthil Mullainathan. And then the second half, I'll talk about some more recent things that have been happening even up to the last few months with with Fan Wei, who's a assistant professor in math at Duke. Senthil and I guess, started this work as large language models became increasingly powerful. We were trying to think about different levels of theoretical abstraction at which you could approach them, right? So there's work that looks down at the sort of circuit complexity level, thinking about the wiring diagram of the transformer, trying to understand how that's working. That's obviously very interesting, very difficult questions. There's work that works at some higher level, treating it as more of a learning theoretic problem. We were interested in sort of trying to come in at some abstraction layer where we asked, what is the problem that large language models are trying to solve, right? Rather than look at their operation, let's ask, what is the task of language generation itself? Because we somehow felt like there wasn't, a sort of ready-made answer to that question, which we found intriguing. And in the same way that, in many areas of theoretical computer science, we try to find, an abstraction layer in which, for example, where cryptography gets reduced to Alice and Bob speaking across a wire while an eavesdropper listens in, it's sort of surprising how much of crypto you can derive just thinking about Alice and Bob and the wire that's in between them. But for large language models, it wasn't clear who the Alice and Bob characters were or what we could say at that level of abstraction. Right, some kind of level at which we might be able to say things that would survive changes to the architecture, changes to the way we go about it. What would that look like? And so we embarked on this, and I want to tell you about sort of how we embarked on this. In the first half, I'll sort of talk about the groundwork for this, and then I'll talk about some recent developments in the second half of the talk. The work ended up, I guess by design maybe, we were aiming for a certain abstract take on this, and the work ended up being quite abstract, but in a way that felt very clean to us. So I'm hoping I'll be able to convey sort of the cleanliness of the model. One of our starting points was to ask, okay, we want to define the language generation problem, right? Let's start there. And if you were to, ask people in the field, what is the problem that language models are trying to solve, or if you ask the language models themselves, what problem are you trying to solve? You would get something like this first bullet point here, right? You're going to give it a large collection of text, and you're trying to build a model that accurately assigns a probability to every possible sequence of words. And we could disagree whether this is the exact formulation of the problem or just something close to it, but this is sort of a canonical way of thinking about what is a language model. It's an approximation to a big distribution over sequences of words. Now, my co-author Senthil, when he was kind of pushing us to think about this, was, often looks at these kinds of formulations, and for some reason his bias is always to be suspect of the role of probability in these statements, right? His argument was, in some sense, the decision to add probability to the story was a kind of modeling decision. That, in his argument, there's nothing inherently probabilistic about the task of language generation. Rather, that was our modeling choice to try to make it tractable. So what would it mean to have a version of the problem that had no probabilities in it? Well, even more abstractly, we could just say, here's a spec for language generation. Design an algorithm that observes strings from an unknown language and eventually begins producing valid strings from the language that have never been seen before. Right? Let's say we took that as our problem. Now, this one seems so ambiguous and so hopelessly general that how could we really get anywhere? But let's kind of sit with that, ambiguity for a little while and just see if we can get somewhere. In this abstract formulation, let's just make some definitions to at least make it, a math problem. So, right, the goal of the algorithm is to utter strings. And this is like strings in the sense of, if you've taken an intro computability class, or even if you haven't, a string is just, let's fix some alphabet like the binary alphabet. It's just a sequence of symbols over this alphabet. And a language simply means an infinite set of strings. Actually, all of our languages are going to be infinite, right? If you want, so you could picture like all paragraphs in English, would be a language, right? It's a set of strings. The strings are the paragraphs. If you want to object that we don't really know what English is, and you wanted a fully well-defined thing, the language could be all strings that are well-formed C programs, right? The C compiler admits an absolute standard on this compiles and that doesn't, so that's the language. Okay. And so, you could, if you want a very concrete question, we'd like an algorithm that I can make up a new programming language with some grammar to it. These are the well-formed programs. I'm going to start showing this thing programs, and after some time, it's going to begin outputting valid programs in this new language I made up. Right? That's what we would like. Okay. So this Sentinel was like, yeah, this sounds good. Let's work on this. And I was like, well, actually, this is well known to be hopeless, this question. Like, this has been tried before. And actually, it's been tried before in what some argue is one of the very oldest results in learning theory, sort of before there was a field called learning theory. This result of Mark Gold from 1967 in a paper called Language Identification in the Limit. So how did Gold's model work? So Gold was interested in how language learning operates. He was partly motivated by computers, but he didn't have access to that many computers in 1967. He was also motivated by how, for example, a 6-month-old infant learns language. Okay? So imagine that language learning is a game played between nature and a learner. Or in our language, we'll call it an adversary and an algorithm. Right? Okay. The adversary is going to think of a secret language that the learner has to identify. And let's say a secret language is known to come from some finite representation. Right? So I think of a secret context-free grammar or a secret finite state machine. Actually, we don't really need the representations. Let's do something even simpler. The adversary says, I promise you that the language is one of this countable list of languages, L1 or L2 or L3 or L4. It's one of those. And the algorithm and the adversary are going to agree that's the set of languages. And basically, we could imagine there's just a giant 2D lookup table, which is if you would like to know if a given string is in a given language, you just ask the lookup table and it tells you. And that's how we agree on the set of languages. Okay? All right. Other than that, it's just some infinite list of infinite sets. Okay. What's the game? The game they play is the adversary takes its secret language and it outputs the strings one by one. And it can repeat them if it wants, but it has to actually output the entire language. And in each step, the algorithm is going to guess what the language is. Right? In every step, you have to guess the language. So this is a guess the language game. So the algorithm is going to guess an index, and the goal is that the language it guesses is the secret language. The algorithm, in Mark Gold's definition, wins the game if there's some step, finite step, t star, such that after t star, its guess is correct forever. Right? In every step after this, its guess is correct. And then we say it has identified k in the limit. It's identified it because its guess is correct. It's in the limit because starting at t star, it's correct forever. Okay? All right. So that's the game. Actually, first of all, we're going to morph the game a little bit, but useful to make sure everyone, are you good with this game? Questions about the game? All right. That's the game. Why was Mark Gold thinking about this? Again, he was actually motivated in part by language acquisition in infants. Because think about a 6-month-old infant learning language, right? Not an 18-month-old, but a 6-month-old. A 6-month-old is pre-verbal, right? They can't verbalize at this point. So there are some rather strong constraints on what the 6-month-old infant can handle. Because, first of all, the parents are speaking in the house in their native language. Or maybe multiple native languages if you want, in which case the language is the union of all the things it's hearing. But let's say they're speaking in one native language. They tend to speak in that language, and they don't tend to speak gibberish. So the infant gets positive examples only. Right? You see a bunch of positive examples. You don't see negative examples. Secondly, the algorithm, or the infant, makes guesses, but at 6 months old, you can't verbalize. So you can't ask active queries like, is this sentence valid? And you can't ever be told if your guess is correct. You're doing this all internally. Right? Somehow, internally, you're learning a whole bunch about what the language is without ever being able to ask questions and without ever seeing negative examples. It's rather impressive that this happens. Right? Okay, so that's the, those are all constraints you're operating under. And Gold's theorem was a negative result, right? This is 1967. There is no algorithm that can achieve language identification in the limit, even for very simple collections, like, say, all the regular languages, all things produced by finite automata. You can't do this. Right, or phrase this way, if I suggest an algorithm, we could construct an adversary that picks a language and gets the algorithm to make infinitely many mistakes. All right. And actually, Dana Anglin came along 10 years later in a paper at Stock 1979 and actually characterized exactly the language collections for which this was possible. And it was a very, very thin set of languages. Actually, I can, if we wanted, I could prove Gold's theorem, but it's not going to be so important for us. Dana Anglin's characterization is sort of interesting. So let me at least mention it on one slide. Here's what Dana Anglin showed, right? So when can a collection of languages be learned in the limit, right? I mean, this is a very hard thing we're asking it to do. So it's going to be a very special set of languages. It's basically languages, as she called it, where each language in my collection has a finite-sized telltale subset. That once you see that subset, you kind of know it's the language. And the way you could picture this is the telltale subset has the property that for any Li's telltale subset is Ti, for any subset of Li that's in the collection, Lj, the telltale subset pokes out of it. It's not completely inside it. Okay? So if you were confused as to whether the answer was Li or Lj, after some finite time, you have seen the entire telltale set and you know it's not Lj. The telltale set comes along and blows away Lj. Okay? That's Dana Anglin's characterization. All right. So Gold's theorem. The thing about Gold's theorem is that he set up a sort of hopeless problem, and then he proved it was impossible, which, while satisfying to some extent, is also kind of what you expected. Like, it's just too hard. And so I, dutifully reported all this back to Sendel as he got excited about this formulation of worst-case language generation. And I'm like, this is why you can't make worst-case assumptions in this area. And so, this is why, for example, you put probabilistic assumptions on the problem. Well, there are many reasons you put probabilistic assumptions. This may be one of them. Okay. But before we gave up, we noticed something interesting, which is this wasn't actually the question we were asking. We weren't actually asking you to solve Mark Gold's problem. We were asking you to generate. And I want to argue that generation is not actually the same as identification. Right, let's go back to the 6-month-old infant. The 6-month-old infant grows up to be a 5-year-old fluent, kindergartner who fluently speaks their language. But obviously, if you asked that 5-year-old to litigate edge cases of English grammar, or frankly, if you asked a 25-year-old or a 45-year-old to litigate edge cases of English grammar, they're going to get some things wrong because none of us really know all the rules of English grammar. In the same way that you see a bunch of Python code in your class and you learn to program in Python, but then you go to a super hard coding interview and they ask you, here's a piece of obfuscated Python code. Does the following, nested double null pointer dereference compile successfully? I don't know. I don't know exactly how Python works. I know how to program in it, but I don't know the exact contours of it. So arguably, none of us have ever identified any of the languages that we speak, be they natural language or programming language. We just know how to generate from them. We have picked a big, safe subset from deep inside the language, and we draw from that. And that's how we generate. It's a different problem. It sort of feels like maybe an easier problem. So let's go back to Mark Gold's game. To our surprise, no one had ever, despite the fact that Gold's theorem has actually remained a mainstay of the language learning literature all the way to the present, somehow people had not gone back and just made this one little change to it. So let's go back and make this one little change to it. Again, adversary thinks of a secret language. This is the same as before. Adversary enumerates the strings of a secret language. One more little piece of notation. Let's say S sub t, at time t, you've seen a sample from the language, a finite-sized sample of t of these strings, one per step. We'll call that S sub t. Okay, but the algorithm, there's a new goal for the algorithm. We're not trying to guess the language. We're trying to generate from the language. So in step t, the algorithm's new goal is to output a string, a sub t, that should come from the language minus what you've seen so far, right? An unseen string from the language. That's what you would like to have. And again, we have all the constraints that the 6-month-old infant has. No negative examples, no feedback on whether you're right or wrong. In some sense, the adversary doesn't actually even know the algorithm is there, right? The adversary is outputting strings. The algorithm sees them and babbles its own strings. And the algorithm hopes it's correct, but it never gets any feedback. The adversary never notices it. It's just saying stuff. Okay? And the algorithm wins if after some step, t star, it's correct forever. Everything it says comes from the secret language. Okay. Now, I guess because of Gold's theorem, we know that if the algorithm is going to win this game, it's going to kind of have to win without ever knowing when it won or how it won, right? Eventually, if it's going to win, it's going to have to start generating from the language without ever really knowing what the language is, or without ever knowing when it has made its last mistake. So that's a kind of like strange way to win a game, but that would be what it has to do. You know, arguably, like, when in your life did you make your last grammatical mistake? Who knows, right? At some point you stop doing it, maybe. Okay, so that's the game. And so we thought, okay, strangely, this game had never been defined before. This seems to capture something fundamental about the generation problem that has nothing to do with, you know, probability distributions or the transformer architecture or anything. It's just the problem of watching words go by and starting to output words that come from the language. So wouldn't it be interesting to go back to Dana Engelin's 1979 characterization and say, which collections of languages allow for generation in the limit? Right? Dana Engelin told us which ones allow for identification in the limit. That's a very hard problem. This is arguably an easier problem. Is it a bigger family, or is it about the same family? And that's a question. So for the first few months when I thought about this, I thought, well, to start, let's come up with an example of a collection of languages where you can't generate in the limit. That would be like the first thing to try. And it was sort of confounding that I could not find a single example where you could not generate in the limit. And that was actually because of a theorem, which we eventually were able to prove. There's actually an algorithm that wins this game for every collection of languages. Okay? So we end up with this result that's way stronger than what we were expecting. There's an algorithm with the property that for any collection of languages, like any collection at all, and any adversary that comes along and enumerates one of them, the algorithm will generate from this string, the language. Okay? Right? So you can always win this game. Right? So this really says it really differs from language identification in a deep, deep way. Right? This idea that I need to find a safe subset to generate from is just a much easier task. And it really does mean this is a genuine algorithm. Right? We'll get to what the algorithm is. It's, you know, it's a very expensive algorithm. But it really means there is an algorithm out there that can see C programs pass in front of it. And after some finite time, it will output entirely just valid C programs. Right? And this is, we're assuming nothing about, the only structure we're assuming about the language is that there are only countably many of them. Right? That's like the one thing that we are assuming about the set of languages. Okay. So that's kind of part one, the statement of the theorem. In part two, I actually wanted to show you more or less how to prove this theorem. And then part three, I will tell you about stuff that's happened since then. Okay. Part two, how to prove the theorem. So an algorithm for generation is somehow balancing carefully between two constraints. First of all, the point again is you only need to generate an infinite subset of this language. You don't need to find the whole language. That's key. And so what you're doing is kind of balancing this trade-off between two concepts. One is validity. You can only generate valid strings. It has to come from the language. And the other is breadth. You're going to have to do this for infinitely long. So you have to output a big subset of the language. Right? Validity versus breadth. And somehow validity, breadth. So like, if you're asked, like, what is this abstract model ultimately going to teach us? And we'll come back to this at the end again. Something about this tension that you have to manage between validity and breadth. Right? Any algorithm for language generation is managing a tension between validity and breadth. And you sort of see this at both extremes, right? What is a failure of validity? It's hallucination, right? It's making stuff up that's not actually in the language. At the other extreme, what is a failure of breadth? It's this kind of mode collapse, right? This collapse onto a very, very thin subset of the possible output set, right? Which is sort of either like just the repeating of certain, you know, tropes over and over. It's a kind of like rigid AI style that's very recognizable. In some sense, like AI slop is a kind of mode collapse. We immediately recognize the AI text because there's not a lot of diversity in the text. Okay, and what's going to happen here is that this model is going to give us some sort of way to start articulating these two concepts in some formal sense and actually looking at the kind of tug of war that takes place between them. The algorithm is going to sort of explicitly use this tension because what it's going to sort of do, we'll see, it's going to start out with a bunch of invalid strings. It eventually is going to learn to sort of avoid those and to sort of thin out to thinner and thinner subsets, eventually so thin that it actually fits inside K, and then it's going to be generated in the limit. Right? That's a very vague kind of picture of what's going to be going on. Okay, and in that way, it's going to sort of eventually win this game. It'll never know quite when it won, but it will eventually have won the game. Okay, so that's the plan.
But there is no feedback if you generate an invalid string.
There's no feedback. Yeah, this is the problem that you face. You're generating strings, and you're like, so is it okay? Am I safe? Who knows, right? That's sort of what's scary about this particular problem, right? You're generating in a vacuum. Now, we could come along and add feedback. That will only make it easier. And there's always this interesting thing between negative results and positive results, right? So for Gold's theorem, which is a negative result, you would want to come and say, how do I make this problem it's impossible. Let's add feedback. Let's add probability distributions, right? When you have a positive result, in some sense, feedback would be nice. This is arguing we don't need it, right? You can do it even if no one ever tells you if you're right or wrong. And that's kind of the, right. So in some sense, with no feedback and no negative examples, we're still doing this. But yeah, that is the scary thing about trying to do this, which is you're sort of saying this into the void, and if you're wrong infinitely often, you lose, right? And how do I avoid that? So there's a whole bunch of things there are a bunch of dead ends, and with a talk twice this length, I could show you a bunch of fascinating dead ends that we went down, which are quite educational, actually. But let me just show you one dead end, because it's the one that was sort of most adjacent to the thing that actually worked. So here's one of many dead ends that we tried. Here's an algorithm that once you see it, you're like, oh, maybe this is going to work after all, right? So the one thing we have going is that the languages are countable. L1, L2, L3, these are my choices. And the true language is out there. It's L sub 50. It's out there. I just don't know what it is. I don't know it's 50. Let's start with the hypothesis that L1 is the true answer. And I'm just going to like stick to this hypothesis until something out in the world proves me wrong. Okay? So as long as what I've seen, S sub t, is a subset of L1, I'm just going to go with it. It's consistent. L1 is consistent with what I've seen. And while that's happened, I'm just going to generate new strings from L1. L1 is infinite, so I can always find a new string from L1, and I'll just do that. Once you see this algorithm, you're like, hey, wait, maybe this actually works. Maybe we're already done on this very slide. Because you can almost imagine a proof that this algorithm works. Here's what the proof would look like. I start with L1, and in general, at some moment in time, I'm guessing that the answer is L sub I. Well, okay, if that's right, I'm all set. If that's not right, then at some point, this enumeration of k is enumerating the entire language. Something will come along and reveal the contrast between Li and k, and we'll know that we're wrong. And then we'll move on from Li to Li plus 1. We're just going to march our way down this list. Right, I believe it's Li. Something comes along to prove me wrong, because the whole language k is being enumerated. I say, oh, I'm wrong. Let's move on to Li plus 1. Now, therefore, I'm going to move down this list, and I'm going to eventually crash into the true language. Right? The true language is L sub z for some z.
What comes along and tells you you're wrong?
Yeah, that's the problem. That's why we have this word wrong in parentheses. Yeah, this is not actually a proof. We'll come back to that. This proof is somehow still useful, even though it's wrong, to kind of get some intuition. If we eventually got to LZ, we'd be fine, because we'd stay there forever. Nothing proves us wrong. But yes, as you are pointing out, there's a problem with this. Maybe nothing's going to come along to prove us wrong. In particular, what is the problem with this proof? Right? There's a lot to like about this proof, if only it were correct. Namely, it has the property that I would, in this telling of the story, I'm winning without ever knowing when I've won. I don't know that when I arrive at LZ, I am destined to remain here forever. It just so happens that I will remain here forever and win the game. Wouldn't that be nice? But there's a problem, which is before I get to LZ, there could be an earlier language, Li, that L sub z is a proper subset of Li. Li is a bigger, actually, for the rest of the talk, I'm going to misuse the words big and small, because these are all countably infinite sets, so they all have the same cardinality in some technical sense. But when I say this says small and that set, I simply am abusing language to say like this one is a proper subset of that one, and there's an infinite amount of extra stuff in that one. Right? So maybe Li has an infinite set of extra elements that LZ doesn't have. The problem is nothing will ever tell me that Li is wrong, because I get positive examples only. Maybe in fact Li is all strings. So I'm just going to see strings. I'm like, there's nothing ever that sits outside of Li. Li might be the answer. And so I sit there on Li and I generate from it. But that means infinitely often, I'm generating things that are not in LZ, and I'm wrong infinitely often, and I lose. OK. So that's a problem. Let me just like redraw this problem here, right? Maybe there's a better way to picture the languages, right? The languages are all bit vectors showing which strings are in them. So L1 has string 1, 3, 5, 7, so forth. L2 has 1, 5, 7. L3 is the infamous language that has everything, which is going to act as a giant filter that's going to catch me when I get there. Like, I'm never going to move on from L3. And the answer here is L5, right? And so first string 12, these are all the strings in the world. U12 gets enumerated. It's in all of them, so no problem there. U9 tells me to move on from L1. I move on to L2, and so forth, right? OK. And so the problem is like, it means when I get to L3, I'm like, things look good. Can I just stay here? No, you can't stay here. You're going to be wrong infinitely often. So I have to move on. But the one thing this algorithm had going for it was that when you got to the true language, you would never be proven wrong and you could stay there forever. And now we've lost that. Because if I have to move on when things look OK, then when I get to L5, I'm going to also have to move on even though things look OK. And now the one thing I had going for me, that this would act as a kind of like safety net catching me, is over. Because now I'm just drifting out to infinity. I'm drifting out to later and later languages. I'm beyond the true language. Now there's nothing to stop me. I'm just drifting out to C, right? So what do we do about that? Well, OK, so that's the challenge. What do we do about that? Something which would be nice, all right, one other brief dead end that doesn't work either. It would certainly be nice if we could find like a, let's call it a minimal language. Imagine there was some language L in my collection that was consistent and was also actually a subset of every other consistent language. Well, then I could safely generate it from it, because whatever the true language is, this is a subset of it. So if I generate from that, I'm generating from the true language. Right? That's sort of the principle we're going to keep using over and over. Like, I can always generate from a subset. You know, if the true answer is the even numbers, and I believe the answer is all the multiples of 8, I'm fine. Because a multiple of 8 is an even number. Safe to generate from, even though it's smaller. And actually, Anglin's condition from way back early in the talk was basically saying you can do identification when you have a property like this. When there is going to be like a unique minimal thing that sits inside all of them is kind of when you can do it. But obviously, that may not happen. I can construct really nasty instances where this is certainly not going to happen. OK, so you play, and then so you think, OK, maybe this is the reason this is just impossible. You go back to try and find a counterexample. You can't find one. And you sort of go back and forth until you stumble across a definition that's like super, super useful. And once you find this definition, everything starts to unravel in this very nice way. OK, so here's the definition that makes everything start working. Let's say a language in my list here is critical if two things. One, if it's consistent, right? Consistent has been like our gold standard. Like everything I've seen is contained in it. Like anything that's not consistent, I just throw away immediately. Like that's easy. If it's inconsistent, I'm just ruling it. Second, any earlier language that's also consistent, right? So if Li is consistent and I comes before N, so this is an earlier language before Ln. If it's also consistent, then Ln is a subset of Li. That's the other property. So L sub n is kind of a minimal language, right? It's the thinnest possible consistent language if I only look back to the beginning, back to earlier languages. Right? I look at L1 to Ln, and at the end of L1 to Ln sits Ln itself. It's consistent, and it's a subset of everything earlier that's consistent. It's like a pinch point. It's a particularly thin language that the sequence passes through, where everything kind of pinches down to it, because everything before it is like a superset of it. OK. Critical languages are super useful. And with critical languages, we can actually just prove this result pretty quickly. So here's a couple of things about critical languages. One, at every step, there's at least one critical language, because the first consistent language must be critical, because there's nothing before it that's even consistent. So kind of emptily, it's a subset of everything. More interesting is this one, right? The true language is going to eventually become critical. Like intuitively, what's going to happen? Here's L5. Let's apply our definition. Is L5 critical? It's consistent, but it is not a subset of L4. So no, L5 is not currently critical, because L4 is over here, and it's not a subset of it. That's a problem. But it won't be a problem forever. Why? Because eventually U5 is going to come along. Right? The adversary has to enumerate this thing. Has to eventually say string 5. That's not in L4, and that blows away L4. It's not consistent anymore. And now suddenly L5 is critical. And that's actually just a proof that works in general. Right? Why is the true language eventually going to become critical? Because consider any earlier language that it is not a subset of, like L4. Well, the true language has something that that earlier language does not have. The adversary has to enumerate L5. So eventually, that string will come along and destroy that earlier language. And after that, the only undestroyed languages are the ones it's a subset of. And so it's now a subset of everything. Okay? So the true language, interestingly, is a pinch point. Right? It's a thin language that everything leading up to it is a superset of it. OK. So that's critical. With that, I can actually tell you the algorithm. Right? This is the algorithm that achieves generation in the limit. What am I going to do? In step T, OK, so here's the algorithm. It's, obviously it's a very expensive algorithm. But in step T, I'm going to consider languages L1 to LT. All right, so I'm going to have this widening window of things I'm willing to look at. In step T, I'm considering L1 to LT. Among L1 to LT are some critical languages. Let's consider the last critical language, right? The critical language that comes as late as possible, but still before T. This is a bunch of critical languages. I'm going to take the last one. And my algorithm is simply generate a new string from that critical language. Okay, so take the last critical language, output a new string from it. That's the whole algorithm. I want to claim this algorithm generates in the limit. Why is that? Well, let's, again, we're allowed to be wrong for some finite time as long as we're eventually right. Let's go out to a time that's late enough that, first of all, so LZ is the true language. Let's remember that. True language is LZ. We're going to go out to a time that's bigger than Z, meaning in this window that we're considering, the true language is in the window. So it's one of our candidates. And we're also beyond this magical time T plus, after which the true language is critical. So we're now at a moment when the true language is in my consideration set, and it's critical. From every step after that, the last critical language comes after the true language. Why? Because the true language is critical, and LNT is the last critical language. So the last critical language has to come after some critical language, so it's after this one. Therefore, critical languages mean you're a subset of every earlier consistent language. So this is critical. This is an earlier language that's consistent because it's the true language. And so the one I'm looking at is a subset of this. But again, it's always safe to generate from a subset. So therefore, if I generate from LNT, I'm generating from LZ. Okay. And that's the entire proof, right? So end of part 2. We have proved this theorem. You can actually generate in the limit for every collection of languages. And intuitively, right, so let's kind of reflect on okay, so that's notationally what the algorithm did. What was the algorithm really doing? It was saying, I don't know what the true language is. It's safer to generate from subsets, so I'm going to try to thin down to thinner and thinner subsets, right? You get in trouble when you say wrong things, so I'm going to try to be more and more rigid in what I'm willing to say. In some sense, this algorithm has a bias that it likes parsimony. It wants very thin sets that nonetheless contain what I've seen so far. And so, as it goes, it's looking at these critical languages, right? Every time it gets to a critical language, it's like, oh, this is uniquely the most parsimonious language I've seen so far that explains what I've seen, because it's a subset of literally everything earlier that's consistent. Later in the sequence, there might be even thinner languages, but let's not worry about that for now. This is the thinnest thing I've seen so far. And so it's drifting further and further, later and later into the sequence, finding more and more parsimonious explanations for what it's seen. And eventually, that will become so parsimonious that it sits inside the true language. We don't know when that will happen, right? That's why you can never really stop this process. But at some point, it will happen. And at that point, it will have won the game without knowing that his has actually won the game. OK, so that's language generation in the limit. Let me talk about, so this turned out to be a very rich model. And there's a bunch of things you can do with it. I want to talk about a few of the extensions and follow-ups. A couple things to observe. One is the algorithm was supposed to output strings, but it actually ended up doing something stronger. The stronger thing is it actually output guesses, right? These critical languages are actually, in some sense, functioning as its guess for the language. Now, Gold's requirement was that your guess, L sub IT, should equal the secret language K. And that was impossible. In some sense, we're like taking Gold's spec for the problem and we're replacing one symbol in it. Instead of LIT equals K, we just want LIT to be a subset of K. That's all. If you can eventually output a subset forever, then obviously you can generate in the limit, because I just pick anything from that subset. Okay? All right. So it's actually doing this thing we might call index-based generation. Now, in the world of language generation that we're mapping onto, elements and indices both have some meaning, right? The element, obviously, is the word you output. The index is essentially the parameters of the model, right? In some sense, L1, L2, L3 are all candidate models for the language you're trying to generate. And the index is the parameter set for that model, right? So as you iterate through indices, you're iterating through basically parameterizations of some model. All right. Let's talk about a few things in increasing order of length. In increasing order of length, I actually left out one little thing. So there are two ways we can ask the problem of generation or of identification limit. One point that Mark Gold made and Dana Engelman made in her paper is The problem of identification in the limit was never a problem of computability. It was not about what Turing machines can and can't do. It was not about the halting problem. It's a question that makes sense even if you allow the, quote, algorithm to actually be a completely non-computable function. Because its problem is not computability. Its problem is it doesn't know what language the adversary is thinking of. And so the questions people tended to ask in that model were actually not about computability. They're like, allow yourself any function at all, there's still an impossibility result. What I've shown you sort of fits that aesthetic, because the one problem here is that in order to determine if a language is critical, I have to solve the question, is this language a subset of that language? Which is actually an undecidable problem. So I've so far shown you something which actually is not quite computable. It turns out you can actually turn this into a genuine algorithm that actually runs in steps on a Turing machine and manages to bypass that step. But that gets complicated, and I'll skip that. There's a question about prompted generation. So far I've shown you what might be called unprompted generation. Your goal is to output just any string. But there's a version of the problem where I show you prompts. I'll show you that on the next slide. And then finally, I'll talk about this idea of breadth, which right. We talked about validity. I've achieved validity. What about breadth? Clearly, this algorithm is engaging in a kind of deliberate mode collapse. It's literally seeking out thinner and thinner, like it's trying to mode collapse in some sense, because the goal was to be valid. What if we wanted to actually balance that trade-off a little better? OK. Let me not say much about prompted generation. Interestingly, this model handles prompts almost effortlessly once you have the algorithm. So you can imagine that in every step, the adversary provides a new string as training data and also a prompt that it's supposed to complete. And the algorithm can't just output any string. It has to output, let's call it a valid completion, C sub t, so that the prompt pt concatenate with ct lies in the language. And the same algorithm we just saw effectively solves that problem also. Stuff about finite collections I'm going to jump over. Let's talk about breadth. So the trade-off between validity and breadth turns out to be a very interesting question in this model. And the question actually becomes quite deep. And actually, after about a year of progress on this, there was this nice Colt tutorial that a number of the people who worked on follow-ups to this. So there was some nice work of Moses Charikar and Chirag Palraju, some nice work of Kalavasas, Morocha, and Villegas from Yale, and then some work I'll talk more about that Fan Wei and I did, all talking about this validity breadth trade-off. And actually, this got nicely wrapped up into a nice Colt tutorial last summer done by 4 of these authors, along with Charlotte Peel, who has a nice paper with Omer Reingold on a different notion of breadth. So this is, yeah, there's a bunch of nice material in this tutorial. Let me talk about one approach to breadth. Right, so we would like to actually generate a lot of the language. We don't want to just generate a small amount. And we can formalize that in the same model in the following sense. There's a true language, and there's an algorithm that's generating ultimately a subset of the language. Right? Let's look at the set of all strings that this algorithm ever generates. Right? That's its output set. We could ask, how much of the true language did it generate? Well, these are 2 infinite sets, so I need some definition that makes sense. And one definition that makes sense is, let's say the function f of n is the fraction of the first n strings of the true language that are in the output. Right? So up to this point, I've outputted a fraction 1 of it. Here I've outputted 1 out of the first 2, 2 out of the first 3, 3 out of the first 4, 3 out of the first 5. I can just look at the fraction of strings I've generated as I go. Now, this is some sequence of numbers, fractions between 0 and 1. So I could ask about the limit of this. This might not have a limit, but I could ask about the lim sup and the lim inf. Right? So the largest number it approaches infinitely often, and the smallest number it approaches infinitely often. The lim sup and the lim inf. And we'll call that the upper density of the sequence and the lower density of the sequence. What I'd like to do is get these numbers to be as large as possible. Now, what we've seen so far among the algorithms, right, which just iterates down critical languages, is an algorithm that actually outputs solutions with density 0. Right? So you have this algorithm, and it's producing things of density 0. And in some sense, like, it's deliberately doing that. It's seeking out these arbitrarily thin subsets so as to satisfy the validity constraint. But in the process, it's getting the 0 density subset. And right, it's passing, as I said at the beginning, through hallucination. At some moment, right, tantalizingly, there's some moment when it actually has the right language. If only it knew to stop there. But it can't stop there. And so it eventually mode collapses. There's sort of this interesting parallel in a very, very distant sense. When I thought about the structure of the solution, I was reminded of my colleague Cristian Nicolescu-Mizel, who with co-authors at Stanford had this very interesting 2013 paper in computational social science on how people acquire the vernacular in an online community. And roughly speaking, in a stylized form, what their empirical findings was that when someone enters a new subreddit and they start trying to post to the subreddit, at first they just sound like a newcomer. Right? There are all these internal idioms that the subreddit uses, and you misuse all of them, and you sound ridiculous, and you don't really fit in. But you stick to it, you keep trying, and at some moment you really sound like a member of the community. You have adopted the vernacular. But then a funny thing happens the longer that you stay in this community, which is the community moves on. New idioms are forming, and you don't pick them up. You sort of age linguistically in the community the way you age in real life. Like, you just can't pick up the Gen Z slang that you used to, that everyone's using, or the Gen Alpha slang, and so you just sound older and older. Right? And you can actually see this happen in time lapse in these online communities that they studied. People don't pick up the new idioms. Right? And there's a funny thing in this sense, because these people are literally starting out hallucinating terminology that is not valid for the community. At some moment, they're just right, but somehow they end up mode collapsing and becoming increasingly rigid. Now, arguably, it's different. Well, first of all, this is a very abstract model. These are human beings. Secondly, here the world is morphing around them. Here we're morphing around the world. There are various differences, but there is this interesting kind of sense that you're passing through these three phases just as we are. And so I was very intrigued by this question, must every solution to language generation limit have this structure? That you're passing, that you pass to something with density 0. Like, this is the bargain you're making. Yes, we can solve this problem always, which is kind of amazing, but the compromise you must make is that you must generate at density 0. And I somehow intuitively felt like it should be true. This would be the satisfying resolution, maybe, to the whole story. But it was not true. And so Fan Wei looked at our work and had these very interesting ideas. We ended up working together and proving a theorem that, again, I found surprising, which is there's actually a positive constant and an algorithm that can achieve generation of the limit and actually output a positive fraction of the language. I can actually output a positive density fraction of the language, which means it must be doing something very different from what the original algorithm was doing. Okay? And we started out with small values, but we can actually push this all the way up to 1/2 in a paper that's appearing at Stock next month. We get up to density 1/2. Okay, let me say a tiny bit about how this works, and then I will conclude. Okay, so the proof of this gets quite lengthy, but let me just give you like a little sketch of some of the ideas that go into this. Because again, we need a totally different algorithm, right? This idea that we're going to just iterate all the way down these thinner and thinner subsets, that's not going to work. So first of all, I could ask the density question even in like index-based generation, where I'm actually guessing what the language is. Imagine the algorithm is just guessing a sequence of languages, with the goal that eventually all my guesses are a subset of the true language, right? They all fit inside the true language. And I could ask, what are the densities of my guesses? What can we say about the sequence of densities of the things I'm guessing? So the first thing you can show is that actually there are instances where your guesses have to infinitely often produce arbitrarily thin subsets. So in that sense, this idea that every solution must look like this, there's a weak sense in which that's true. Infinitely often, your guess has to have 0 density. And there's an example here which is not going to be crucial for the rest of the talk, but something where you have no choice but to make bad guesses, right? 0 density guesses. That doesn't rule out the idea of generating a positive density, though, because as I make these bad guesses, that's not the end of the story. I get to output things for infinitely long, and I'm only graded in the limit of what did I eventually say. So just because in step 1000 I happen to be guessing a very thin language doesn't really matter, because in step 1000 I say literally one string. As long as I recover and guess denser languages, I might be okay. Right, so just because I make a bad guess every now and then is fine. So we should actually ask, like, what about the lim sup of my densities? Can I eventually return to high density guesses? As long as I can oscillate between low density and high density guesses, maybe this is all going to actually work out. And that's actually what we end up being able to show, which is this theorem. And this, again, is sort of the surprising thing. Let's say that an index-based generation algorithm is accurate in step t if its guess is exactly right. Right? If in step t it satisfies Gold's condition. Then there's actually an algorithm which achieves generation of the limit, like we saw before, and also is accurate in an infinite sequence of time steps. That's the added feature that we can actually have. Okay, so this is an algorithm that comes sort of as close as possible to, right? Mark Gold wanted that after some finite time, you're correct in every step. That's impossible. This is, after some finite time, you're always contained in the language, and infinitely often, you are the language. Okay? once you have this, you can make progress toward actually getting high density. It's hard to do this, right? Because the whole reason we're iterating down the sequence of critical languages, I don't know which of these things is the true language. That's my whole problem. And so the way to safely make sure I'm never invalid is to just keep moving out to later and later languages. In order to achieve this, I have to somehow have a mechanism that backs up, right? So I like parsimony in my models, but I also have to somehow like expansiveness in my models, right? And I end up, and so this algorithm has to somehow zigzag. It goes further and further down here, but infinitely often it actually comes back and actually touches this language. The danger with coming back infinitely often and touching this language is you can't go one more step back because this language is too big, and then you'll be wrong infinitely often. So it has to come all the way down, further and further out, and come back and touch this without ever exceeding it, right? And that's what this algorithm is doing, right? Okay, and once you have this, then things start working because effectively, infinitely often, you have the chance to actually output from the true language, and that's what's giving you the chance to output at positive density in some very high level sense. Okay, we're approaching the time to wrap up. So let me conclude with some thoughts here. So we start with this spec, right? Design an algorithm that observes strings from an unknown language and eventually begins producing valid strings from the language never been seen before, right? A very informal, very vague description of language generation. But it turns out to be possible to actually make this precise, right? Mark Gold already had a version of this 60 years ago, and if we start from there, we can actually say something. And it turns out that you can really generate from an unknown language knowing only it comes from a countable list of candidates. And it has the structure where we're sort of passing through, initially we're invalid, and eventually we mode collapse to theorem and theorem subsets. But these results on density say there are better algorithms, even in this very model, where we're infinitely often backing up toward denser languages, and we can actually achieve a constant fraction of the entire language. I think the interesting question here is, this whole framework is obviously extremely abstract. The upside is this theorem continues to be true even if we throw away transformers and replace them with some next generation of models. This is not a circuit complexity theorem. It's a theorem about the literal spec of language generation, right? And that obviously is both the interesting part of the result and also the challenge in mapping this onto what we actually see in language generation. And I think, if we're trying to do that mapping, I think this axis from validity to breadth is maybe a guide to how we might try to map this onto what's going on. And in particular, I think this idea of breadth has been quite interesting and quite sort of productive in thinking about language models more generally, right? The idea of a sort of rigid AI style and the idea that some models seem to have less of that rigid style than others is some informal notion that breadth is maybe an axis along which we can try to measure things. So if I'm going to leave, sort of with one open question, which is not a theoretical question in this model, of which there are many, but is a more a question about the interpretation of the model, how might we actually try to operationalize this notion of breadth? Right? This idea that it's possible to generate more widely from the language or very narrowly from the language in a way that we might actually be able to discern differences in the way language models are operating. And I think in this way, this model has been sort of a fascinating source of ideas, not just for us, but for a number of people who've built on it and followed up on it. I think it suggests a lot of interesting questions going forward as we sort of think about this really fundamental question of what does it mean to operate in this generative mode? What does it mean to engage in generation? And all of the interesting questions that I think we can grapple with on that going forward. Thanks very much.
Okay, I'm sure we have questions. You pick that person who should.
First, I have to see someone asking a question. Yeah. Oh, you're looking for a microphone, yes.
So it seems like the positive examples are all like enumerated from the secret language for all your for all the results, right?
That's the idea. So the adversary thinks of a secret language, and they have to output only from that.
So what happens if like a complete enumeration does not happen, like a subset, the positive examples?
Yeah, great question. Somewhere here I have a slide in these backup extra. There we are. Yeah, so there's been a bunch of follow-up work on that question actually, some of which is appearing at Colt and Stock, I think. So the first one is, suppose the adversary only enumerates an infinite subset of the language. Then in fact, there's this nice work of Bai, Panagrahi, and Zhang showing that you can actually, and actually this was sort of implicit in the Charikar and Pavaraju work, that you can actually still achieve generation in the limit, which is actually a much stronger statement, right? It's enough to see an infinite subset of the language, and then you produce an infinite subset of the language. Ironically, the thing you produce is not a subset, right? So the adversary outputs an infinite subset C. The interesting thing is, if you look at what you generated, it's not a subset of C. It's a subset of K, but it's not a subset of C. So C acted as like a clue to what K was, but it was not the subset you're generating from. And then we could actually extend our density result to say, if C has density alpha, you can generate density alpha over 2, basically, again, using this clue. And then there's this interesting recent results of Raman and also Merocha et al. Looking at what if you can actually go outside the language, right? What if the adversary can occasionally introduce corruptions, right? So the 6-month-old infant listens to their parents speaking, and occasionally those parents make grammatical errors and say things that aren't in language, and the algorithm is surviving a sort of asymptotically small fraction of that also. Yeah. Yeah, question. Christian. Yeah.
I'm trying to think of a practical application of what you're describing.
Yeah.
And I think, let's say I've gone to an international tourist location, and I overhear people speaking a language.
Yeah.
And I try to guess what language did I just overhear.
Yeah.
Is this similar?
That's a good question. So you could argue that that's Gould's problem, right? So Gould's problem is basically, I don't know what this language is, but I'm listening to it. And I'm trying to guess what the language is. The generation problem is you're there and you're going to begin trying to say some simple phrases. So you watch this for a while, and now I'm going to be able to say some simple phrases. I never know quite what the language was. One interesting example is actually with bilinguality. So I was talking about this with someone who had been reading our paper, and they said, like, there's an interesting, they're like, this told them something interesting about their child who they were raising bilingually in English and Hindi. And the thing was, their child understood English and Hindi at this point, but they only spoke in English. You'd speak to the child in Hindi, they would answer in English. And he's like, maybe what's going on is they're looking for a parsimonious way to generate, right? Like, the correct language is English Union Hindi, but you don't need English Union Hindi. They have somehow collapsed to just English, which is also consistent, right? It's also a valid way to generate, but somehow it's not. Anyway, so yeah, I think there are these interesting questions about, yeah, if I think about these analogies, that, yeah, absolutely.
A question that I have, something that was confusing to me, was it seemed that like when the model is generating from the language, it has to generate something that it hasn't seen from the adversary. But how, if the model can't identify the language, which is like the Gould's problem, how hard is it hard for the model to actually do that?
So the key thing there is, at any given time, the model has some guess of the, I think this changes slides very fast, so let's go back to, yeah. So at any moment, the model has a guess what the language is. And it also has access to this lookup table of like what strings are in that language that it's currently guessing. So its guess could be wrong, but it's like I guess the language is L sub 10. I have a lookup table for L sub 10. So what I'm going to do is just start going through strings until I basically crash into a string that's in L sub 10, and then I output that one. I agree. We'll never know. It'll never know if L sub 10 was the true language, but at least while that's its guess, it's going to generate from that. Yeah.
Thank you.
Yeah, Stuart.
So this is going to be a very 50,000-foot question.
Sure, yeah.
So if I think about the transition from Gould and identifiability to Valiant and probably approximately correct.
Yeah.
The initial definition of PAC algorithms is they output an H.
Yeah.
So it's keeping the identification idea, right? You're supposed to output something that's the right language.
Yeah, yeah.
So if I do the analogous step from where you are to a PAC version of where you are, are all of those results already known? Have they already done all that? Or are there new things we could do with this weaker idea?
Yeah, there's actually this interesting, I'll just put the citation up out of context. Yeah, so actually, one way we tried to move this into a PAC world, I won't try to read everything on the slide. We tried to move this into a PAC world by looking at finite collections of languages, so we actually have a finite size input. You actually get new things. So there's this interesting paper of Lee, Raman, and Tiwari, which followed up on what we were doing, that basically was like, what if I think about pack learning in a generative setting, right? Where there are many valid answers to something, and I'm going to look for a pack-like guarantee, but not where my goal is to output a hypothesis, but to generate from the distribution. And you actually end up getting new questions there, interestingly. So it seems like if I add distributional assumptions to this, which this didn't have, and I say, but my goal is not to find a hypothesis, but to actually generate, then for some reasonable definition that would contain our problem in a probabilistic sense, you actually do get some interesting new pack questions. Yes. And this would be the paper to look at.
Right. You should get lots of things that we thought were hard, maybe are now easier, because that's sort of what you showed.
That's sort of what's happening, is that generation is just easier, yeah. And so certain things that had obvious pack lower bounds may now have some, be more tractable. Yeah, good question.
I have a question,
okay.
Which is that in real life, do we really have this infinite sequence of languages? So I want to have you thought about how to relate that to the concept of the universal language, where sort of all languages are actually related to this universal language, which...
Yeah, it's a good question. I mean, I guess I would argue, do we have infinite many languages? Like, again, the cleanest instantiation of this, of course, would be like programming languages, I think, right? Where every programming language has some grammar that says these are the syntactically well-formed programs in this language. And yeah, I guess in some very real sense we have an infinite family of those languages, right? Because it's not hard to make very complicated grammars. I could do that forever. I would get more and more complicated languages. There's an infinite set of them. And so I don't think like the idea that they're infinite many languages poses any profound conceptual problems here. You could say, well, realistically, the largest grammar I'm ever going to use is this size, right? Which is, again, what motivated us. I keep finding myself pointing to this slide that I didn't use in the talk. You know, like, what if it comes from a finite collection, right? What if I say my collection of languages, and I can just tell you the slide since you may be curious. Like, what if I tell you, I promise you, it's generated by a grammar of size with at most k productions to it? Then I have a finite collection of languages. Now, if we go all the way back to Dana Englund, one result of her characterization was that in the finite case, you can solve identification. And you can sort of see why from that broken algorithm. What I would do with the broken algorithm is I would topologically sort these languages by inclusion, which means every time I encounter a language, there's nothing before it that was a superset. And so my broken algorithm now works, right? And that's sort of the proof. One interesting thing, though, from what they were doing is that you can't look at my collection of languages and give an a priori bound that I promise you that within 1 million steps I will have succeeded. I can't tell you I will have succeeded by this time. There are simple examples of that, right? And with generation, you can, right? So with generation, I can look at the collection before the adversary has started enumerating anything and say, I'm going to give you a number t, and I promise you that if I see t samples, I will start generating correctly forever. And so generation has that extra sort of uniformity bound. And actually, that was the wormhole by which Lee, Raman, and Tiwari started to connect this to pack learning, right? That uniform bound is the analog of a sort of pack bound in some sense. And they had this thing called the closure dimension, which sort of characterizes that for a language family. So yeah, so I think there are interesting questions with the finite case, but yeah, I think they're both natural.
There's some sort of polynomial versus complexity questions.
Yeah, so there's this interesting paper by Pablo Barcelo and his co-authors that says that this bound that I give is like sort of horrendous in the state complexity. So if I tell you like this is a finite automaton on at most n states, I believe, and I would apologize if I'm misquoting this, that the upper bound you can give is like doubly exponential in the size of the state set. I mean, first of all, the number of automata is singly exponential, and this can be exponential in that, basically. So it blows up quite rapidly. Yeah, some of these guarantees come with bad complexity bounds. And I think one interesting question is, are there interesting special cases where we can get, say, polynomial bounds? Very, very natural question. There's some work that Omer Reingold and Charlotte Peel and I have been doing on mistake bounds that actually argues that if I'm not thinking about when I make my last error, but just how many errors I make along the way, then the bounds look much, much better, actually. So, yeah.
I don't see more questions. I have bad eyes. So do you see more questions?
I also don't, yeah.
OK, so let's thank Jon again.
We could talk offline, yeah. It sounds good. All right, thanks very much.